Hello all, my name is Ashutosh Rastogi. I'm a teacher by profession. My mission is to impart quality education for all. For that purpose, I'm creating these videos. If you appreciate my work, then please do like my video and subscribe my channel so that I could get the motivation to prepare more videos. Anyways, in this particular lecture, we're going to discuss about the analysis of quantization error for the linear quantization when the input signal is a sinusoidal type. So these are the outlines. We'll start off with the introduction where we have discussed what we have learned in our previous lectures. Then we will going to calculate the signal to quantization noise error in the pulse code modulation for uniform quantization having the sinusoidal type of input. I mean where the input signal is a sinusoidal one. Then we're going to take up a numerical problem in which we'll try to formulate a basic foundation how to tackle numerical problems related to the PCM. We will try to discuss a general problem where we will try to discuss all the possible variations. So in our last lecture, we have evaluated the expression for the quantization noise power as the normalized noise power would have been calculated as delta square over 12, where delta is the uniform step size. The expression for the normalized signal to quantization noise ratio in the PCM is also being evaluated, and it has been calculated as signal to noise ratio will be equal to 3p upon x max square into 2 to the power 2n, where p is the signal power, x max is the maximum exposure of the signal or the peak value of the signal, and this small n represents the number of bits required to encode the sample value. This is what we have evaluated in our last lecture. So the normalized signal to quantization noise ratio in PCM in dB would have been calculated as signal to noise ratio in dB should be less than or equal to 4.8 plus 6n. Please recall that in order to calculate the normalized signal power, we have put x max is equal to 1. So in that case, the expression of SNR in dB would have been calculated as this one. So in this lecture, we will try to find the expression for signal to quantization noise ratio in the PCM, which have at the input side as sinusoidal input signal. So obviously we should know that in order to calculate the signal to noise ratio, we need to find out the signal power as well as the noise power explicitly. So in order to calculate the signal to quantization noise ratio for the input signal, let us assume that the input sinusoidal signal to the PCM is being given as x of t will be equal to am times of sine of 2 pi fmt, where am is the amplitude of my message signal and fm is the frequency of my message signal. We know that in any electrical circuit, the power would have been calculated as V square upon R. So the power of the given signal would have been calculated as V square upon R, where V is the root mean square value of the signal and is being given as Am over root 2, and R is the resistance. So now putting the value of V in equation 1, we have P is equal to Am over root 2 square into 1 over R. So at the place of P, we have put this Am upon root 2. So the final expression would be equal to Am square upon 2 times of 1 by R. So the normalized power would have been calculated as, in order to calculate the normalized power, the resistance should be equal to 1, or we have to put resistance value R should be equal to 1. So in this case, the normalized power will be given as P is equal to Am square upon 2, where Am is the peak amplitude of my message signal, which is nothing but a voltage signal. So the normalized signal to quantization noise ratio in the PCM would have been given as signal to noise ratio is equal to 3p upon x max square into 2 to the power 2n. This expression we have already evaluated in our last lecture. So hence in this expression we have to put p is equal to am square upon r and x max is equal to am. So now putting these values in equation 2, we have signal to noise ratio would have been evaluated as 3 times of am square upon 2 into 2 to the power 2n upon am square. So at the place of p, we have put it this expression am square upon 2, and in place of x max we have put am. So finally it would have been evaluated as 3 by 2 times of 2 to the power 2n. So 3 upon 2 again turns out to be 1.5, and the final expression would have been calculated as 1.5 times of 2 to the power 2n, where this small n represents the number of bits required to encode the sample that we have already discussed. So now the expression of the signal to noise ratio in dB would have been calculated as signal to noise ratio in dB will be equal to 10 times of log base 10 signal to noise ratio. This is the basic definition of representing any quantity into decibel. So signal to noise ratio in decibel will be equal to 10 times of log base 10, 1.5 times of 2 to the power 2n. So again, by applying basic property of logarithmic, we have signal to noise ratio in dB will be equal to 10 times of log base 10, 1.5 plus 10 times of log base 10, 2 to the power 2n. So we have applied the addition property of logarithmic. Then further, it would have been solved as signal to noise ratio in dB will be equal to 1.76. Since log base 10 1.5 will be equal to 0.176 multiplied with 10, will be having 1.76 plus 2n times of 10 times of 0.3. The value of log 2 we are assuming as 0.3, although it is equal to 0.3010, but for the sake of simplicity we are only taking 2 decimal places, that is equal to 0.3. So this would have been evaluated as signal to noise ratio in dB will be equivalent to 1/8 plus 6n. For 1.76 we have written as approximately as 1.8. So the final expression of signal to noise ratio in decibel would have been evaluated as 1.8 plus 6n. So this is the required expression for signal to quantization noise ratio in the pulse code modulation system when we have a sinusoidal input. The calculation of this expression would be quite easier if we have understood our last expression quite well. And just for your general knowledge, I would just like to mention that this question once have been asked in IES examination. So now we will going to discuss the numerical problem. So a television signal having the maximum frequency of 4.2 MHz is transmitted using binary pulse code modulation system. Given that the number of quantization levels are 512, then we need to determine, in the first part we have to determine the code word length, then we have to calculate the transmission bandwidth, in the third part we have to calculate the final bit rate, and in the final part we have to calculate the output signal to quantization noise ratio. So in order to solve any numerical problem, first you need to mention what are the parameters that has been given in our question. So we need to write them explicitly. So the given parameters are the highest frequency component FM will be equal to 4.2 MHz and the quantization levels L will be equal to 512. Since the number of bits to encode a sample and quantization level are related as L is equal to 2 to the power n. Here L is the number of levels and n is the number of bits that is required to encode a sample value. So just putting values, what we are left with 512 is equal to 2 to the power n. So in order to solve that we need to take the logarithmic. So by taking log, what we are left with, n is equal to log base 10 of 512 divided by log base 10 of 2. So we are left with 9. This could again be simplified as log base 10 times of 2 to the power 9, which would have been written as 9 times of log base 10 2 upon log base 10 2. So that would further simplified as 9. So this is the value of our code word length, n is equal to 9. So this basically signifies that in order to code a sample value, we will be using 9-bit code word. So in the second part, the transmission channel bandwidth would have been given as bandwidth should be greater than or equal to n times of FM, where FM is the maximum frequency component of the signal and n is the number of bits required to encode the sample or the code word. So on putting values, the bandwidth will be equal to 9 times of 4.2 megahertz. Just because FM is equal to 4.2 megahertz, it is given, and the value of code word N is equal to 9 we have already evaluated. So while putting these values, the bandwidth would have been calculated as it will be greater than or equal to 9 into 4.2 into 10 to the power 6, which would have been finally evaluated as bandwidth should be greater than or equal to 37.8 into 10 to the power 6 hertz. So this is our final answer. So in the third part, the final bit rate is equal to the signaling rate, and the signaling rate R would have been given as R should be greater than or equal to n times of Fs, where Fs is the sampling frequency and n is the code word. And for the Nyquist criteria, it is already known to us that Fs should be greater than or equal to twice of Fm. So the final bit rate is equal to the signaling rate and is given by this particular expression. So let us say this is our equation number A. So as we had already mentioned that the sampling frequency will be greater than or equal to twice of Fm. This is the Nyquist criteria that we have studied in our sampling theorem. So the sampling frequency would have been calculated as it should be greater than or equal to 2 times of 4.2 megahertz, where 4.2 megahertz is our maximum frequency component. So Fs would have been calculated as it should be greater than or equal to 8.4 megahertz. So now in order to calculate the value of the signaling rate, we have to put the value of the sampling frequency in equation number A. So R would have been evaluated as 9 into 8.4 into 10 to the power 6 bits per second. So here we are using this equal to sign, which basically represents the minimum bit rate required. So that turns out to be 75.6 into 10 to the power 6 bits per second, or 75.6 megabits per second. So this is our answer. So now in the fourth part, the output signal to noise ratio would have been given as signal to noise ratio in dB will be less than or equal to 4.8 plus 6n. So generally student might get confused that where we have to apply the formula as 4.8 plus 6n and where we have to apply the formula 1.8 plus 6n. So it is quite simpler. So you just only need to focus out that whether the input signal or the given input signal is a sinusoidal one or not. If it is strictly mentioning that we are assuming sinusoidal signal, then we have to put the value 1.8 plus 6n. But since in our question it has not mentioned, so we have used this particular formula. So please be focused and you have to read the question properly. So now on putting values, since the value of n is equal to 9, so we have signal to noise ratio in dB will be less than or equal to 4.8 plus 6 into 9. So we are left with signal to noise ratio in dB will be less than or equal to 4.8 plus 54. That is finally signal to noise ratio in dB would have been calculated as it is less than or equal to 58.8 dB. So this is the final expression for signal to noise ratio. In general, in the PCM numericals, generally these parameters that we have discussed so far in this particular numerical would have been asked. Generally you need to find one or two values. So the tip to solve the PCM problem is you have to read the question cautiously. You need to write down what are the values that is given to you and what are the values that you need to solve out. So once you state those values, you can apply the proper formula and get the results. And please make sure that you should not do any mistakes while converting linear to dB and dB to linear. Please do practice it well. Problems related to PCM are quite simpler. If you focus, then obviously you can solve all the problems. So these are the references. Thank you very much for your patience here.